Hello everyone, welcome back to NPTEL lecture series on cycloaddition reactions. So we have been talking about 1,3-dipolar cycloaddition between various dipoles and dipolar. So today we will continue our discussion on 1,3-dipolar cycloaddition, and this time between azides and alkenes and alkynes. So like any other dipole, azide is also a very good dipole in 1,3-dipolar cycloaddition, and it has found various applications in organic synthesis. The first report of 1,3-dipolar cycloaddition between azides and alkynes was reported by Ralph Housgen in late 1950s, and if you see, the reaction between azides and alkenes will give 1,2,3-triazolene, whereas the reaction between alkynes and azides will give you 1,2,3-triazole. So this is the azide and this is the alkene, and this, when you heat it, you get the corresponding 1,2,3-triazolene. Likewise, when you do the same with alkyne, you get 1,2,3-triazole. So this was reported late 1950s, but renaissance of this 1,3-dipolar cycloaddition of azides took place sometime in 2000 and afterwards. Okay, I will come to that little later. Let us now go and see the regioselectivity of this 1,3-dipolar cycloaddition reaction between azides and various alkenes and alkynes. So when you look at this azide, you can see here the terminal nitrogen has large LUMO coefficient, whereas if you take alkene, and this terminal alkene has large HOMO coefficient. So this is what actually determines the regiochemical outcome of this 1,3-dipolar cycloaddition reaction. So that's why you predominantly get 1,5,1,2,3-triazolene. And here again you can see here, so this also will give this product, and if you look at this product again, you can see there is a formation of a double bond and the pyrrolidine ring is missing. So that means what happens is, after the 1,3-dipolar cycloaddition reaction, initially you get this intermediate. So now this reaction is being done in acetic acid. So the protonation of the pyrrolidine nitrogen will take place and followed by elimination, because once it eliminates, you see the aromaticity is retained. So that's how the elimination of pyrrolidine helps to get the aromatic compound. When a nitrogen is attached to the aryl group, so you have the azide and one of the nitrogen is attached to the aromatic ring, that particular nitrogen is known to have more nucleophilic character than the terminal one. So now you can see this azide. So this is the terminal nitrogen and this is the nitrogen which is attached to the phenyl group. So this particular nitrogen is known to have more nucleophilic character. So then that will determine the regiochemical outcome of the product. Moreover, it is not only that nitrogen, but also the substituents or substituent present in the dipolarophile, that also will determine. Here in this case, the dipolarophile has an electron withdrawing group. So that's why you get 1,4 adduct, whereas when you have electron donating group like the earlier two cases, and you see you will get the corresponding 1,5. So the numbering is done like this: 1, 2, 3, 4, 5. Similarly, you can write here 1, 2, 3, 4. So this is 1,4 triazolene. This is 1,5 triazolene. Okay, and we have several examples. And if you look at this particular example, you start with enamine, and then enamine reacts with aryl azide. So that should in principle give this 1,5 triazolene. and likewise again you can see this is the enamine, and this enamine reacts with tosyl azide to give this particular triazolene. Again it is 1,5, and if you look at this substituent, this dipolarophile, it has two substituents. That means at this carbon you have a cyanide, and at the other carbon you have 2-trifluoromethyl, and here the 2-trifluoromethyl actually determines the regiochemical outcome in addition to this nitrogen attached to phenyl group. So that is why this is the major product, which is with respect to cyanide it is 1,5, but with respect to the trifluoromethyl it is 1,4. This type of 1,3-dipolar cycloaddition can also happen with the sterically crowded azide. For example, if you take this azide, so this is attached to a quaternary carbon, and this type of azides normally made by whenever you have an epoxide like this and then treat with sodium azide, you can do an SN2 opening of this epoxide. So you will get the trans hydroxy azides. This upon 1,3-dipolar cycloaddition with alpha chloroacrylonitrile. Okay. So first the 1,3-dipolar cycloaddition takes place, and to give this compound, now you can see it can undergo elimination of HCl in situ. If that happens, then it will give this very interesting the triazole. Okay, it is cyanotriazole. And we also have seen intermolecular reaction, and this reaction is known in intramolecular way also. So for example, if you have an azide like this and the double bond which is attached and connected to this azide, so if you heat it, this can undergo an intramolecular 1,3-dipolar cycloaddition to give this type of bicyclic 1,2,3 triazolene. Here there is no question of regioselectivity, since both are 5-membered rings. This type of 1,3-dipolar cycloaddition has been applied in total synthesis. However, it is not applied to make triazolenes, but the triazolenes have been converted into aziridines. So let us see how this has happened and how this 1,3-dipolar cycloaddition between azides and alkenes have been successfully used in total synthesis of natural products. So for example, an azide like this can undergo an intramolecular 1,3-dipolar cycloaddition with this 5-membered lactone. When that happens, so you get this corresponding triazolene, and this triazolene immediately it can undergo ring opening to form one side N minus and other side N2 plus. As you know, N2 is a good leaving group. The N minus can intramolecularly attack and kick out the N2. That means from 1,2,3 triazolene you can make aziridine. Okay, so that is what happened, and once you have this aziridine and it was converted into isometamycin, a very interesting natural product in few steps, and also metamycin in the process. So the successful synthesis of this alkaloid metamycin depends on this 1,3-dipolar cycloaddition. So that is about 1,3-dipolar cycloaddition between azides and alkenes. How about 1,3-dipolar cycloaddition between azides and alkynes? See, for example, if you take this bis azide and treat with dimethyl acetylene dicarboxylate. This is dimethyl acetylene dicarboxylate, which we have discussed a lot in Diels-Hall reaction. So this can undergo spontaneously when you heat it to form the bis triazoles. Okay. Here there is no question of regioselectivity, because the triple bond, that is the acetylene which you used, has two esters, and so it is a symmetrical dipolarophile. So there is no question of regioselectivity. Okay. Likewise, when you talk about intramolecular 1,3-dipolar cycloaddition between alkynes and azides, then also the regioselectivity does not come into picture. So, for example, if you take this tosylate and this alcohol, and when you treat with sodium hydride, it will pick up this hydrogen, it will form O minus and kick out this tosylate. So, you get this propargyl ether, and this propargyl ether, when you treat with sodium azide. So, sodium azide, what will happen? It will open the epoxide, you will get azido alcohol. So, what you get is basically you will get this intermediate when azide opens the epoxide, and that will undergo an intramolecular 1,3-dipolar cycloaddition to give this triazole. So, since this is intramolecular, so the regioselectivity is okay. However, when you have intermolecular 1,3-dipolar cycloaddition between alkynes, like Diels-Sol reaction, where we also talked about retro Diels-Sol reaction, when you take this substrate and then do a 1,3-dipolar cycloaddition with benzyl azide, so this can undergo a 1,3-dipolar cycloaddition between this double bond and this azide. So, basically what you get is so now this can undergo a retro 4+2 to give furan and the other substituted triazoles. Okay. So, this is possible because this we have already discussed in retro Diels-Sol reaction, and similarly you can see the same in retro 1,3-dipolar cycloaddition reaction. Again, if you look at the dipolorophile is symmetrical. Okay. But when you use alkyne or any unsymmetrical alkyne, then you do not get the regioselectivity unlike alkenes. For example, if you take phenyl azide and phenyl acetylene, and if you heat it, you get almost a 1:1 mixture of 1,5 and 1,4 triazoles. So, why we do not get selectivity unlike the alkenes? So, this is because the difference in HOMO-LUMO energy of azide and alkyne is almost at the same level. Okay. When there is no difference, then what will happen? Either alkyne or azide can control how it is going to react in the 1,3-dipolar cycloaddition. So, that is why when you do this reaction, you get a mixture of 1,4 and 1,5. You can take just benzyl azide or electron donating phenyloxy group, always you get the corresponding 1,4 and 1,5. Here one oxygen is missing. Yeah. So, how to get exclusively only one? So, the 1,3-dipolar cycloaddition between alkynes and azides was reported by Rolf Eusgen in late 50s, but it took about 40 years to come back and revisit this chemistry and then get exclusively one isomer, and that process is part of a broad name called click chemistry. So, click chemistry, actually there are many reactions which can come under click chemistry. Since we are talking about only cycloaddition, we will restrict only to cycloaddition. So, even the Diels-Sol reaction can come under click chemistry and 1,3-dipolar cycloaddition between alkynes and any azide is also called click chemistry. Only difference is earlier cases, if you have seen, you take an azide, treat with alkyne and you heat it. Here, instead of heating, you use a metal salt. Okay, use a copper sulfate, copper 2, and then use sodium ascorbate and then water. What is important is water. Okay. It is done in aqueous solution. Of course, mixture of organic solvent and aqueous solution. The sodium ascorbate is the one which reduces copper 2 to copper 1 in the reaction mixture. So, that actually triggers this 1,3-dipolar cycloaddition. When you do this reaction under this condition, you get exclusively 1,4 triazoles. 1, 2, 3, 4. So, that is the beauty of this copper chemistry, copper based click chemistry, and because of this Barry Sharpless got second time Nobel Prize, and as you know, first time he got Nobel Prize for his important contribution on asymmetric oxidation, Sharpless asymmetric epoxidation, dihydroxylation, amino hydroxylation and so on. Okay. And if you take this example, and again if you use copper 1 directly in the presence of diisopropylethylamine and solvents like acetonitrile, you can get again 1,4 adduct exclusively. So, that is the beauty of this click chemistry, where copper plays a very important role in bringing this dipole and dipolar file together, and this dipolar cycloaddition happens. So, in short, if you look at when Huygens developed this 1,3-dipolar cycloaddition between alkyne and dipole, he got a mixture of 1,4 and 1,5. But 45 years later, when Sharpless reported, only change he did was he used the metal, and that is copper, and copper 1 really helped in improving the regioselectivity almost to only 1,4 adduct and not the 1,5 adduct. So, let us see what was the mechanism proposed by Sharpless. So, Sharpless proposed first the copper takes out this acetylenic hydrogen, and it forms the copper acetylide, and this copper acetylide then again, as you can see here, it forms a bond between copper and this nitrogen, and now this undergoes cyclization to form this 6-membered ring. So, basically one can say oxidative addition, and the last step, this is the oxidative addition, and this is the last step, that is reductive elimination to get the triazole and again the copper. And it took about 17 years to propose another mechanism, which is now the most accepted one. Here, according to this mechanism, first copper coordinates with the triple bond. Okay, the copper coordinates with the triple bond. That is the first copper which coordinates with the triple bond. Then the second copper actually removes this acetylenic hydrogen, and you can see there are 2 coppers here. Okay. So, now it reacts with azide. Okay. When it reacts with azide, what happens? The N minus reacts with this copper, which is coordinating with the triple bond. Okay. Now, the triple bond attacks the azide. So, basically that leads to the 6-membered ring, and when the 6-membered ring is formed and this nitrogen, that is the internal nitrogen, attacks the double bond and the copper comes out. Okay. So, still this copper is intact, okay, that will release the copper again and form the triazole. So, this is the well accepted mechanism for the click chemistry between terminal alkynes and azides initiated by copper 1 catalysts. Okay. So, there are several examples, we will discuss a few today. So, you can take aryl azides and a triple bond which is attached to guanidine like substrate, then this can undergo 1,3-dipolar cycloaddition to form this 1,4 triazoles, and likewise this phthalimide N-propargyl phthalimide, this upon click chemistry with benzyl azide, it can form the corresponding 1,4-triazoles. So very easy to form, such triazoles, and this can be done at room temperature. You don't have to heat it. Just what you need is take copper sulfate and then treat with sodium ascorbate in tetrabutadiol and water. Or if you don't want to use sodium ascorbate, directly take copper iodide in the presence of diisopropylethylamine and the solvents like acetonitrile. You can do the same thing to get the corresponding triazoles. Okay. This particular reaction is well applied in carbohydrate chemistry. Okay. So, for example, you can have the fully protected sugar with an azide at the anomeric center. So, now if you do the same click chemistry with phenylacetylene, you can see the corresponding 1,4-triazole. Okay. It's a very simple and straightforward reaction, and you can see here in this particular example, it is the other way. In the first case, the azide is attached to the sugar. In the second case, the triple bond is attached to sugar. So, now in situ, when you take the substrate and then treat with TBAF, TBAF will remove the trimethylsilyl group. So, that is how you generate the acetylene, and that undergoes the click chemistry with cyclohexyl azide to form this 1,4-triazole. Actually, the report by Sharpless on this 1,3-dipolar cycloaddition between alkynes and azides using copper salt actually triggered the click chemistry, and the number of publications coming out of 1,3-dipolar cycloaddition increased dramatically. So, that is how he got second Nobel Prize. Again, you can see another interesting example from sugar. So, you take D-glucose and then peracetylate, then remove the anomeric acetate with bromide, and then do an SN2 reaction with sodium azide and do the click chemistry. You can get this corresponding 1,4-triazoles, and we can also attach to terpenes. For example, if you have menthol and then do the propargylation, and then you treat with a mixture of benzyl bromide and sodium azide. So, what happens in situ, it forms benzyl azide. Okay. Benzyl bromide reacts with sodium azide, it is a one-part reaction. It forms benzyl azide, and then instead of copper acetate or copper sulfate or copper iodide, one can use copper based nanoparticles and then heat it. So, this also can give the corresponding 1,4-triazole. This is another interesting example actually reported from our group. So, where you have alkyne attached to the furanose ring, and now you can treat with various azides. Here it is just benzyl azide, and this gives the corresponding 1,4-triazole. And likewise, you can do the same thing with the pyranose ring, and the pyranose ring also will give this corresponding 1,4-triazole. Okay. So far we talked about 1,3-dipolar cycloaddition between one azide and one triple bond. Suppose you have a substrate already having an azide and alkyne. So, now can you think of doing a click, double click? So, that means, for example, in this case you have an azide and a triple bond. If you heat it under high temperature, there is a likely possibility that this can undergo an intramolecular 1,3-dipolar cycloaddition. But now between this triple bond and azide, we know that azide is more reactive. So, under this click chemistry condition, if you add an external alkyne, okay, for example, if you add methyl propylate, this in principle should undergo a click chemistry between this methyl propylate and the azide. So, one can initially expect this triazole. Once this reaction is over, Now you still have a triple bond. Now what you can do is you can also add another azide. Okay. So now when you add an external azide, this external azide and this triple bond under the same condition can undergo one more 1,3-dipolar cycloaddition to get this bis triazole. Since you take this methyl propylate and this parachlorophenyl azide a little excess, so what will happen always at the end of this reaction, in addition to this bis triazole, you will get this as the pi product, because this azide and this triple bond will also undergo 1,3-dipolar cycloaddition, that is click chemistry, to get this pi product, but both are separable. So what is key is in this particular reaction you have an azide and the triple bond in the same substrate, but by doing the click chemistry, by adding sequentially first a triple bond followed by an azide, one can do two click chemistry in one part. Can you introduce organometallic group in the click chemistry? Yes. For example, if you start with ferrocene having an alkyne, so now this alkyne can undergo a click chemistry with this type of azides, and you can see this azide is derived from an amino acid. Okay. So earlier we saw click chemistry on carbohydrates, now you can see click chemistry on amino acid. When you do the same thing on amino acid, then you can see you can extend this to peptides. Okay. So this is quite simple and straightforward to get this 1,4-triazole. These 1,4-triazoles can be a good linker between the corresponding organometallic compound, that is between ferrocene and amino acids. So this is another amino acid ester. So having an azide, so this also can undergo intermolecular 1,3-dipolar cycloaddition to give this type of 1,4-triazoles. So earlier example we discussed about the formation of bis triazoles starting from a molecule having both azide and alkyne, and we can also do a bis triazole by starting with bis alkane. See, for example, if you take this the dibromonaphthalene, okay, now if you do a Sonag-Mishra coupling with the TMS acetylene followed by removal of the TMS with potassium fluoride, you get the corresponding bis alkyne. Now this bis alkyne, if you treat with excess azide, okay, for example this type of azide under click chemistry condition, now it can form bis triazole. Okay. And it is known that this type of compounds can be the mimic of antimicrobial peptides. So after the click chemistry became famous, so there are many natural product like molecules which were synthesized using this click chemistry, and it can be done in large quantity, because when you do any 1,3-dipolar cycloaddition between azide and alkyne, if you heat it beyond certain temperature, for example if you heat it beyond 80 degrees, because of azide which is known to be explosive, such reactions should be carried out very carefully. Okay. But after the click chemistry concept came into picture, all these click reactions are done at room temperature. So that way this opened up a new area wherein lot of such click chemistry has been done on natural system. Okay. So with this I will stop here about 1,3-dipolar cycloaddition between azides and alkynes, and then the next lecture I will talk about whatever the leftover examples of 1,3-dipolar cycloaddition between other dichlorophiles and dipoles. Okay. Until then, thank you.